Hello everyone, welcome to the physics tutorial. Today we are talking about refraction. Okay, I think that this is the phenomenon. It's easy to see everyday life. You can just go to kitchen and get a cup of water and a spoon or a fork or a knife, and then you will see this phenomenon in water, of course. Okay. And then for this one, I think if you remember, we did something in year 9. You might have observed this one before. Okay, so let's have a quick recap about the refraction. Remember when you were year 9, this is on our side pad. You put a half circle glass here, and then you shine a light, okay, from any angle, say for example 30 degrees. It's coming here, and then here is air, and this is glass or plastic. Okay, and then you found that the angle becomes smaller, and then you measure the angle here from normal. I think everyone remember this one, and the angle becomes smaller, and then you change it. You make it a half circle glass here, so now this is glass, and you shine a light, so light won't change direction here, also 30 degrees, and then when it comes to air, the angle become bigger. So normal light, the angle become bigger. If we give them a symbol, this is a theta I incident, okay, and this is theta R reflected, theta I and theta R. And then what do we find? We can find smaller than theta I, and then this one is theta R is greater than theta I. Okay, you try many angles, and then you find that this is a general pattern. And then we will say when the light is traveling from air to glass, the light is bending toward normal. Okay, and similarly, when light is traveling from glass to air, and the light is bending away from normal, so bending toward and bending away. Why does this happen? We need to know in year 12. You need to know because the speed of light is slowing down. So I would say slowing down from air to glass. They slow down, and then of course from glass to air, speed of light increase. Okay, speed it up. Okay, this is slowing down, and this is why cause the direction of light change. To take one more step about this one, to define the index of refraction, we define, I put 3 bars here, means definition. This is speed of light in vacuum, and this is speed of light in the medium, the transparent media. I think you know the speed of light in vacuum is C, and for this one vacuum, okay, so C is 3 times 10 power of 8 meter per second. And then if we apply the definition, so N will be what? N will be C over in vacuum. Now we are in vacuum, okay, and of course the number is 1. Okay, easy. So there's no unit for refractive index. And now if we say the speed in air, okay, this is very similar to vacuum. Okay. N is 1.0008, but we normally treat it as 1. Air is similar to vacuum. But if we go to water, the speed by measurement is 2.254 times 10 power of 8 meter per second. And then if you put this number into our definition, N equals to C over V. So you put it here. C is speed of light, 3 times 10 power of 8 in vacuum. And in water is 2.254 times 10 power of 8. And then you see our calculator, then you get the number is 1.330. The number, I think at the moment, you know, is greater than 1. Okay, greater than 1. And that means the speed is slower. And then another one we can see in common sense is glass. So for glass is about 1.912, even slower, meter per second. And N is how much? N is 1.568. So okay, in terms of speed of light. The slowest one, diamond. Okay, the speed of diamond, the light is 1.1240 times 10 power of 8 meter per second. And then n will be what? N will be 2.41. Okay, so it's really slow. So that's why diamond the reflective index is big. That means it can bend the light more. So that's why diamond looks so colorful, a lot of kind of rainbow color there. Okay, you don't need to remember these numbers. Okay, these numbers will be given. Okay, so you don't need to worry about it, but you need to know how to use it in calculation. And now I think this is the phenomenon, like the experiment and the phenomenon you can see. And then now we want to use another way to understand this one, which is I need to use wavefront to understand refraction. For example, we have a medium. So here can be, say, air, and here is, say, water. And we have a light. Okay, the light is traveling from here. So we got one direction. And if we use wavefront to see this one, okay, I draw normal first. If we use wavefront to see this one, and what is the wavefront? Okay, and you can see wavefront, I think we know this already, so it's a lot of peak. So when we join the peak together, so this is our wavefront. You can have an imagination, think that there's a group of army, so this is their head, and they are marching toward to water. So someone is hitting the drum in the side, dong, 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 dong. So this is the frequency. Okay, so this is how they work. And in general, in air, army can travel faster, and then in water, they become slower. The first army here, when he touched the water, this one slow down. It's we say wavelength. Okay, or the step becomes smaller. So this is our, say, lambda, and the lambda becomes smaller here, smaller. This person here, this in air, okay, so still work a very big step. So this one is still big step, okay, but this one becomes smaller step, so it's bending here, and then they move a smaller step, and this one still move in a big step, so it's closer and it's still bigger. So this side is still working big, but here slow down, and then gradually they turn to here in this direction, smaller here, but then bigger there. But I think you get the idea. This side they slow down first, so the wavelengths start to become smaller, and here keep the bigger movement. So that's why they change direction, and that's why when they slow down, it's bending toward to normal. Another way to explain the refraction. Okay. And then, of course, when they travel from lower speed area to higher speed area, it will be bending away from the normal. Okay, so this is when we use the wavefront to understand refraction. Now, another thing we need to talk is apparent depth. And what does that mean? Basically, if you check our first picture, so you will see the bar is slightly like floating up, or it's bending. So I'm hoping to use the feature to explain this one. So assume we have water here and this land here. Okay, we got the feature here and we have a fish here. Okay, and the person can see the fish, so we have a light. Okay, so traveling from here, going to the person. And you know we need to draw normal, am I right? And because it's in water and air is here, so the speed become faster. So they will be bending away from normal. So we do this one. It's bending away from normal. The angle become bigger. So this is our theta I, and this is our theta R. It's bending away from normal. So theta R is greater than theta I, as we learned. And what will happen here? This light go to the person, am I right? We know already. And the person will feel what? The person will feel the light is actually come from straight line, so it's here. So the person looks like what? Fish is coming from here. So this is the real fish, and this is the image or apparent fish. So if the person try to use the fork to aim the fish, if he aim here, you'll never get the fish. But if the person studied the physics, and then he will know the real position of the fish is below the image, So he can see the image here, but if he aim lower, and then he will be able to get the fish. Okay, so studying physics is quite important. That will help you get the fish. So now we check another story, same story. So we got a person here, we got a fish here. Okay, the fish can see the person. Okay, now we draw normal. And because the speed is slowed down, so the light is bending total to normal. So the angle becomes smaller. This one. So this light is coming to fish. And the fish will see what? The fish will think, oh, the person is come from here. Apparently, okay, the person come from here. And if the fish doesn't study physics, it will think, okay, the person is actually quite far away, so it's quite safe. But actually, okay, if he study physics, he will understand that the person is actually quite close. The real person is here. So it's very dangerous for him to run away. And do not think the person is quite far away, quite safe. So for a fish, if it study physics and he understand the danger and opportunity, it's become a surviving skill for it. Okay, I hope you enjoy this story. And this is about refraction and about apparent depth. Okay, can be look further or closer. Okay, finally, okay, we come to the end. This is very important for year 12 for Snell's law. We don't need to know how we get this law, okay, but I think basically Snell did a lot of measurement, a lot of calculation, and he find the conclusion. Okay, the conclusion is n1 sine theta 1 equals to n2 sine theta 2. Okay, and what does that mean? Basically means here's the boundary and this is the normal, and I got a light incident ray coming here and comes to here. And for the refractive index, this is n1, this is n2. The incident angle theta, say 1, the angle coming out is theta 2. And this formula applies. Okay, remember sine and cosine theta. We will see an example about how to use this formula, but this is the idea of Snell's law. How do we explain refraction? I think the basic way to do this one will be refraction occurs because light changes speed when it moves from one medium into another. Okay, or you can write when light wave move from one medium into another, it changes speed and the change of direction can be observed. And now let's see an example. If we come to NCEA previous questions 2018, we can use this example. She noticed that the light refracts. Okay, so you see the keyword refracts. Now define refraction. So how do you do it? The keyword that you need to do is the change in speed. That will change direction. Okay, so do that properly in your own word. Now, the diagram shows the cross-section of the glass looking down from above with the juice inside. For the purpose of this question, you can assume the glass itself is very thin, so we can ignore the glass. One completed diagram clearly shows the refraction ray index. So this time, I think we need to use a ruler. So get a ruler, and then this is the incident ray. And you know it's from air to juice, so it will slow down to the glass. It will slow down, so it will be bending toward the normal. Okay, as long as you make the angle smaller, that will be okay. So this is the theta r. So we did the first one. Now you need to calculate the angle of the refraction. So now I think you know already. Apply Snell's law. So n1 sine theta 1 equals to n2 sine theta 2. And now we put the number in. Okay, assume this is number 1 and this is number 2. So n1 is how much? n1 is in the air. Okay, in the air is 1. And juice is what? Juice is 1.34. Okay, so we put the number 1 in air. And sine is how much? 62 degree. And n2 is in juice 134 and sine theta 2. So we want to know the angle theta 2. So do it slowly. So sine theta 2 will be sine 62 degree 1.34. So theta 2 is how much? Is arc sine bracket sine 62 degree 134. And then use your calculator. So you get theta 2 is 20.5 degree. Okay, so this is how example showing us how to apply Snell's law. Okay, let's summarize what we have learned. From here, assume this is the media 1, this is media 2. The wave is traveling from here into here, and you can see the lambda, the wavelength become shorter. So now, because V equals to F lambda, and F is the same, so V1 is greater than V2. And you can see the speed of the wave slow down. So if we draw normal, and you see the angle becomes smaller, so it's bending total to normal, theta 1, theta 2. So theta 1 is greater than theta 2, so it's bending total to normal. And more specifically, for the Snell's law will be N1 sine theta 1 equals to N2 sine theta 2, Snell's law. Hope this makes sense and is helpful. We'll see you in the next tutorial. Okay, thank you very much.